Okay, you probably know me. My name is Eric Derouane. I am born on July 4th, 1944, and I'm always happy to come back to the US in July for my anniversary. Um, well, I did most of my education in Belgium, and started my university education in 1960. Now, you probably may wish to know why I picked up chemistry as the field of my action. In fact, my father was a professor of chemistry in high school, and my mother was a professor of English. And quite rapidly, I like to learn sciences and biology and physics and chemistry, and I believe I was about 12 years old when I decided I wanted to become a chemist. In fact, history may probably repeat itself, because I now have a daughter, and when she was 13 years old she told me that she wanted to become a chemist, and she's now at the university and going on for a chemistry degree. Well, nevertheless, I started my university at Liège in Belgium, and I went for what we call in Belgium a licence degree, which means 4 years of chemistry. First 2 years more or less general chemistry, and then you sort of specialize in physical or analytical or organic. And I decided to go for physical chemistry. Now, when I was in my 3rd year, I decided to come as a trainee over the summer in the US, and I spent 2 months working for Allied Chemical in Morristown, New Jersey. And at that time, the director of the lab in Morristown was a man by the name of George Joris, who himself had graduated from Princeton. And George Joris told me, well, that Eric, you have a choice. You do either polymers or you do catalysis. And he told me, well, and I can give you a good recommendation in Princeton for either field, but you must choose between these two. So I went back for my last year undergraduate in Belgium, and I made up my mind, and that was catalysis. And then I left in September '65 for Princeton and started my graduate work under Professor John Turkovich. So my main area of research at that time was to work on adsorbed species and trying to identify the molecule surface interaction using techniques such as EPR and NMR. And quite a few papers came out of that work. They may be all now buried down in the scientific literature. But in any case, that's where I got my first exposure to NMR spectroscopy, which has become, as we all know, a very important technique, and one which is still very dear to my heart. After about 2 years in Princeton, this was of course the time of the Vietnam War, and I'd moved to the US with an immigrant visa, which was a rather difficult situation because I was drafted and was given notice that I had to leave for Vietnam within the next 2 weeks. So I didn't like that too much, and immediately called the Belgian embassy in Washington, and they say, well, there is nothing you can do really. Either you go to Vietnam or you go back to Belgium. And with no problem, that was perfectly legal. So I went back to Belgium and finished my graduate work at the University of Liège, where I got my degree, my doctor's degree, in '68. In the meantime, however, I had met my wife in '65 in Princeton. She's French, but that may be why I met her in Princeton. I was looking for some company. And so in '68, when I graduated from the University of Liège, we got married, and my first job, in fact, was at the Atomic Energy Center in Saclay, where I had the opportunity to do NMR research with Professor Abraham, who is very well known in the area of magnetic resonance, both electron paramagnetic resonance and nuclear magnetic resonance. Then after 1 year in France, I came back to Belgium. That was '69. And that was also the time when Michel Boudard was visiting on a sabbatical the University of Louvain with Professor José Fripia, who is now in the US. And that's where I met Michel Boudard for the first time. And he was giving a course in Louvain, and I was writing the course for him. And he invited me to spend 1 year in Stanford. So in July '69, I left for Stanford to work with Michel Boudard. And that was the time where he had visitors like Bob Garton, who was just about moving to Exxon, where another student at that time was Ricardo Levy. And so I sort of met, when I was in '69 in Stanford, what I would say was the basic crew of what is now Catalytica in Mountain View. And that's how far I get in my relationship with these people. My research topic with Michel Boudard at that time was, well, he asked me to develop magnetic resonance in his lab. And of course you need a chemical problem, and he was in catalysis. So I helped at that time to solve a problem dealing with the rather unique activity that magnesium oxide had for the H2D2 exchange at very low temperature, liquid nitrogen temperature. And that was the first known system that was working at such a low temperature without involving transition metals. So the problem was quite interesting, and we struggled for about a year. And finally we were able to evidence at the surface of magnesium oxide defect centers, paramagnetic centers, which were perfectly doing the job. I was very happy in the recent literature in reading a paper by Manfred Barnes on magnesium oxide doped with lithium, that he was referring to our old work and even sort of postulating that one of these centers could be the one responsible for the activation of methane. Well, I don't know whether it's true, but it's nice to be called 20 years later. And at least that particular work has never been questioned. It's still of really good actual value. In fact, I may come to that point later on this tape. I have a renewed interest in magnesium oxides that can do beautiful things, but as I say, we'll come back to that later. Okay, so after my stay with Michel Boudard, so I left Stanford in 1970. Then I moved to the University of Liège, where I was a assistant professor. I was mostly doing EPR studies on catalysts and complexes in zeolites, non-stoichiometric compounds, and these type of problems. That was also the time when I had an interaction with José Fripia in Louvain before he left for France. And that's the time where I got my first exposure to zeolites. In 1973, a position, a professor position was opened at the University of Namur, very close to Liège, but every close is, all universities are close in Belgium. They can't be too far from each other. And there was the opportunity there to start a new lab in catalysis with rather powerful means in the field of NMR, EPR, also terminal analysis. And I got an offer from Namur which I accepted. So I moved there and started from scratch, but the university was quite rich, so that was of a great help. And I would say that in about 2-3 years, the lab was really fully operational. We were working on problems like ferromagnetic resonance of a divided metal, like nickel or cobalt, looking at steam reforming catalyst, also looking at iron deposited in magnesium oxide in relationship with ammonia synthesis. And that's the period where I first got acquainted with industry, because it so happened that in 1970 I had also met in Stanford Henrik Topsøe, the son of Aldo Topsøe from the Topsøe company. And in 1975, Henrik Topsøe called me and asked me whether I would like to do some consulting for them. And of course I said yes, and that's how I got involved with my first industrial contacts. So then my activities more or less split it in two directions. One was still the NMR research applied to catalysis and catalyst, which I was doing in Namur, and the other was some research I was doing for Topsøe, which has never been published, unfortunately, but they have made a lot of money with it, dealing with methanol catalyst, water gas shift reactions, and ammonia synthesis. Well, our work on NMR and salt species studied by NMR was progressing well, but we immediately realized that to get good spectra without getting bankrupt, I mean by using carbon-13 enriched molecule, you needed supports that would have a large surface area. And of course we could prepare oxides like magnesium oxide or alumina or even titania with a specific surface area of about 200 to 400 square meters per gram, but still the ideal supports were of course zeolites. And so we started at that time to look at reactions occurring on zeolites by NMR and in situ. And the first reactions which we looked at were butene isomerization. 1-butene to 2-cis and trans-butene, nothing very exciting, but at least we could test the method, we could test our materials. And that's how we got into zeolites, because an important problem when you do NMR on supports is that you want to avoid paramagnetic impurities, to avoid broad lines. And of course, if we use commercial zeolites, we have a lot of iron in it, which is not too nice. So we needed to prepare our materials. So now we were into zeolite synthesis. So we had NMR, zeolite synthesis. We were also equipped for thermal analysis. And I believe we were very fortunate, because in 76, 77, that was also the time when ZSM-5 came out for the first time, at least in the public literature. And although we didn't have much experience with zeolite synthesis, I decided that we should prepare ZSM-5, and we were in fact the first, I believe, to report on the methanol to gasoline conversion using ZSM-5. So that excited a lot of people. This was the start of a whole history of ZSM-5. We passed the recipes we used to various colleagues, and suddenly ZSM-5 was everywhere, and this has been a very exciting time. So we diversified our research at that time. Zeolite synthesis, and mostly ZSM-5 synthesis, was rather a big share of our work, not only in terms of preparation but also in terms of characterizing intermediates in the synthesis. The other area where we got involved was the study of surface reactions on ZSM-5. That of course included the methanol conversion. We tried very hard to look at the way by which the first carbon-carbon bond was formed, but we failed, like everyone I believe since then. We concentrated ourselves a little bit more into ways by which we could limit the reaction to the production of olefins. We also looked into xylene isomerization, and then we were, I would say, about in '79, and that was when I was offered by Exxon the possibility to spend 1 year in Linden as a sabbatical visitor. So for about 1 year, while my lab was still running in Belgium, and where I was calling it every 2 or 3 days just to keep informed of what was going on, I had the chance to work in Linden at Exxon with Terry Baker. And lots of people know, of course, about the beautiful work that Terry has been doing with this in situ electron microscope. And it got me quickly excited about the technique. And what I was interested in was sort of to develop a model for the phenomena that he was observing in terms of metal support interactions. Carbon gasification had been observed. All these particles moving on the surface of carbon or whatever support had also been well studied by Terry. But then I came with the idea that maybe we could explain all these behaviors by phenomena like wetting and spreading of metals, which were below their Taman temperature. And that in fact was not only true for metals but also for oxides. So we did work on the system of nickel on carbon, nickel on graphite, iridium on graphite. We also looked at copper oxide on magnesium oxide. And we came up with models which were rather interesting. Like, for example, in the case of iridium on graphite, we proposed a model for the iridium particle on the carbon support that we call the hardcore model. Nothing to do with pornography, but still hardcore. In fact, we had quite a few problems with Exxon management because they wanted to change, and they didn't want it to see hard. They wanted to see solid, but we told them that solid was not necessarily hard. So there we were with the hardcore model, and the idea was that the iridium particle, which was on the graphite, had mobility, because when it was in the presence of hydrogen, the heat absorption of hydrogen on this very small cluster releases a tremendous amount of heat, so that the surface of the particle becomes soft, whereas the interior is still hard. So you have some sort of a vanilla ice cream ball that's floating on your plate, and that's how we did visualize the iridium particle. Then for the nickel and carbon system we also had a rather interesting model whereby we could see the depletion of the nickel particle as it was channeling to the graphite. And at some point the nickel had totally disappeared, and of course that was a question, where has nickel gone? And then we did a few experiments whereby we could reoxidize, oxidation reduction treatment. We could regenerate nickel particles that were laid down on the graphite surface, but along the channels. So in fact, we got a patent on that, which was about the redispersion of nickel in catalyst, where you could have graphite or coke present, and that I believe has been practiced. And then of course, as we had the hardcore model, we had to have the softball model, and that was another one which we proposed for copper oxide on magnesium oxide, where we could really see sort of volcanoes erupting when we were reducing or oxidizing these particles. In fact, all that work that was done at Exxon has now been published in Journal of Catalysis, and these papers can be found in the literature, let's say, between 1980 and 1982. Well, after my sabbatical at Exxon, I came back to Namur, of course, and got back into my academic shoes and did a lot of progress with zeolite synthesis. That's where also we tried to tackle other zeolite systems. That's also the time when I proposed with Dr. Gabellica what we called molecular traffic control, a process in which different molecules, molecules which differ by their size and shape, can travel along different channels in zeolite structure. So it is sort of a type of molecular shape selectivity, but here with the idea that you will separate the molecules in these channels based on their size and shape. Like if you have a city with small streets and large avenues, where the trucks and big cars would preferably travel in the big avenues, whereas the smallest car would preferably use the small streets. By the way, that proposal was a matter of controversy for a rather long time. I would say probably until about 1987, and it had pro and con and fans and detractors. But in 1987, some papers started to appear, NMR papers, mostly by the group of Vega at DuPont, supporting molecular traffic control, and of course I was very happy about that. And very recently the idea and its use have been claimed by Dow, by Juan Garces from Dow, as the reason for which mordenite, which has been acid leached, in which we have developed cross porosity between the main channels, is an extremely good active and selective catalyst for synthesizing 4,4' diisopropyl biphenyl. And it's specifically quoted in the paper and in the patent that molecular traffic control is important, so I have all reasons to be happy about that discovery. Okay, nevertheless, so that was in the early 80s, where we were working essentially on a lot of concepts, trying to enlarge our base of zeolite materials, where we were starting also to do what I would call the premises of quantitative aluminum NMR and silicon NMR as applied to zeolites. And that was altogether very exciting. But I I was contacted at that time in '81 by Paul Weiss, who was a director of Central Research at Mobile, and Paul asked me whether I would like to join Mobile. And of course Mobile Oil was, I would say, on top of the research in the field of zeolite. And I decided that yes, I would make sort of this quantum jump and leaving academia for industry and leaving Europe for the US, everything happening at the same time. So I joined Mobile in June 1982, and I was rather quickly offered a rather good group in zeolite synthesis, with also the opportunity to do other things on the side, and I would say that this was really a very exciting professional life. Of course, I had to work on zeolites, but as I say, I could also do other things. And although the management was not too keen, I decided I wanted to enter the aluminophosphate-based materials. And obviously, one thing to do was to introduce silicon. So I was working at that time, before the actual patent from carbide came out. They only came out late '83, early '84. I was working on SAPOs at Mobile, but I decided that I wouldn't approach the problem from a classical viewpoint, because I realized that silica had a low solubility at low pH, which is essentially what you do when you synthesize aluminophosphates, and therefore borrowing from phase transfer catalysis from colloidal chemistry, I thought that it would be better to approach the synthesis of such material by what I have called, and that has been patented, the two liquid phase synthesis route. And that really consists in having in the synthesis system two liquid phases present, in addition to, of course, the solids which you may need. One essentially that would bring in that particular case, the aluminum and phosphorus, and the other one, a organic phase, typically hexanol, which would bring in the non-soluble compound in the aqueous phase, that is silicon, which we would supply as a organic agent. Well, there have been real development, because not only have we applied that to silicon, but we have also prepared materials whereby we could introduce into the aluminophosphates elements such as iron, antimony, vanadium, titanium, etc., with rather good success. So we had there a generic method for preparing SAPOs, and I would say that probably the material at this time for which it is best is SAPO 37. In the course of this work, we also discovered quite a few materials which received names, of course, and they can be found in the patent literature under the names MCM 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc. And well, MCM just stands for mobile crystalline material. That's all it means. Nothing very strange behind it. And the numbers just refer to the order in which they were discovered. Some of these materials had structures analogous to the union carbide aluminophosphates, but others didn't. And typically such a material which was made in March 1983 was one which we called MCM9. That was a SAPO, silicon aluminum phosphate molecule sieve, and its diffraction spectra didn't fully match any known spectra for aluminophosphates or silico-aluminophosphates. So we were rather confident that we had something new, and the patent was applied for. Well, I continued this type of work until about 1984, where I would say for family reason I decided to move back to Europe. I went back to Namur, to my former lab. I maintained, of course, some contacts with Mobile and with other industrial relationships I had had, and continued my work in zeolite synthesis. At that time, in our research in zeolites, we expanded our field to first large pore materials. I wanted to go into an area where we would progressively move away from ZSM5. There were too many people working on ZSM5 by that time. But I was more interested in materials like Supper 37, ZSM20, zeolite beta, special forms of mordanite. Also, I had a personal interest for molecule-zeolite interaction and trying to model a little bit better molecule-zeolite interaction in terms both of visualization but also theory. And these were the basic two activities in the field of zeolites which we pursued. Also, we had the chance of having a new NMR, so now we had a 200 MHz NMR and 400 MHz NMR, so we did a lot of development in aluminum NMR applied to zeolites, and we were faced with the problem of quantifying the behavior of quadrupole nuclei and how we could do two-dimensional NMR in zeolites. And that has been some work of which part of it has been published, a lot more will be. That was performed with the Topsoe company, and it deals with the investigation of de-illumination phenomena, steam enhancement of the activity of zeolites. And I would say that we have now been able to propose a model whereby we can see framework aluminum that's progressively dislodged from the framework can turn into a pentacoordinated aluminum which finally is expelled as an octahedral aluminum species. Even more interesting, what we have noticed is that we can dislodge the aluminum up to a certain point, even where to the point where it is almost pentacoordinated, and whereby by a simple treatment with water in hydrothermal conditions we can reinsert aluminum in the framework exactly in the position where it was before. So it means that you really can rejuvenate to some extent a ZSM5 catalyst which has been deactivated by steaming, for example, like it can occur if you use it in the methanol to gasoline process. Well, with respect to molecule zeolite interactions, as I said, this has now become a personal problem. First of all, I had the idea that when we talk about a molecule in a zeolite, the molecule is neither a gas nor a liquid nor a solid. It is interacting with the zeolite framework. And so that's when I came out with the what I call the nest effect, molecule nesting in zeolite. What I thereby meant is that both the geometry of the molecule and the geometry of the receptor site on the zeolite had to adjust to each other. Like, for example, if you lie on your bed, the mattress will give up a little bit and you will just relax in your bed, and the better is the accommodation between yourself and your bed, the longer you will stay in bed, probably. And that was the basic idea I had behind the nest effect. That is, if a molecule and its zeolite environment like each other, they are likely to interact a lot more, and maybe this may lead to higher catalytic activity and selectivity. Now, about a year later, I was discussing with a friend, a colleague, a physicist, a theoretical physicist in Namur, who had been working on the occurrence, formation and stabilization of helium bubbles in the walls of nuclear reactors. And he had developed a beautiful model to explain why bubbles in such a metal would organize themselves as arrays, and it was all based on van der Waals interaction. Then one day I showed him a zeolite, and he said, well, it's just like my bubbles in my nuclear reactor walls. It's just they are connected, but why don't we apply the same model that I used in my own problem to your problem? We can describe the zeolite as a sum of bubbles separated with walls, and if you put a molecule into a cavity, its matter within a cavity is the inverse of a bubble into a solid. And so after a few beers, and well, I would say a lot of beers together, we finally decided that we had to agree on something, and we worked on a paper which appeared, I think, in 1987 in Journal of Catalysis, which was called the confinement effect. And the idea of the confinement effect was that once a molecule is in a zeolite, the van der Waals interactions are amplified because of the curvature of the surface, and as a result, the physisorption energy, it's physisorption because it's van der Waals interaction of the molecule interacting with its environment is tremendously magnified. In fact, the model predicts that the amplification factor can reach a factor of about 8. That means that if we look at typical heats of sorption, for example hexane, that would sorb on amorphous silica with a heat absorption of 10 kilojoules per mole, well, if you now absorb it in a zeolite where it is really confined, like for example in ZSM5, you will have heat absorption of about 70 kilojoules per mole, which is the real physisorption energy, and it's also the one that you can measure. Well, just for historical purpose, when we submitted this confinement paper to Journal of Catalysis, the British editor, I don't know who the referees were, but at least I know who the editor was. We got 2 very nasty referees report. These guys wouldn't believe that you could indeed have a magnification of the heat of physisorption by a factor of 8. And that, of course, was troublesome. But then we said, well, the theory cannot be wrong. That was the attitude of my friend the physicist. So we must find a way to convince the referee that we are right. Then we did a literature search, and we went backwards and backwards and backwards to the very origin of and the first theories of adsorption. And sure enough, we had not done our homework properly the first time, because we found a paper by de Boer, published in 1930, where de Boer had already predicted this enhancement by a factor of 8. Of course, he didn't have the nice equations which we have, he didn't have the full picture which we had or were proposing, but he had suggested the factor of 8. So our reply to the referee was extremely simple. We sent him a reprint or a copy of the paper by de Boer and told him de Boer was right, so we must be right, and you must allow our paper for publication. And that was about all the discussion we had with the referee, and the paper was accepted, and it has been published, and I believe has attracted quite a bit of attention since then. Well, of course, this was the theoretical approach to molecule zeolite interaction, and we wanted to go a little bit further, and that's how I got also involved in molecular graphics and trying to describe with these new graphics tools the molecule zeolite interactions in more quantitative terms. We have been doing, following that, Monte Carlo studies and molecular dynamic studies of water in materials such as ferrierite, and these are studies which we are still pursuing at this moment. Well, I should now go a little bit backward in the history, because in 1987 Mark Davis at a symposium in Nijpoort in Belgium reported for the first time about a material which he called VPI5. And I was attending that meeting, and also was Roland van Balmoos, who had been working with me at Mobile. And Mark Davis showed the X-ray diffraction spectrum of VPI5, and immediately Roland van Balmoos and myself just were sort of shocked, because we recognized many of the features which we had observed in the material that we had prepared in 1984 under the name MCM9. And Mark disclosed, of course, the structure, which was the 18-member ring structure, which we had not recognized. We just recognized it was large pore, but as very often in industry, you have no time to to look at structures, just produce materials, that's all. Nevertheless, after that we went back to the bench and did quite a bit of work on what we had called MCM9, and finally succeeded in preparing it very pure. And of course we had the silicon containing material, so that was not the aluminum phosphate material that had been first disclosed by Mark Davis. So sort of we had a material of our own, and Mobile decided to go after that for a patent, and we got what we have named finally the XYZ patent, where X, Y, and Z can be anything, any element that will fit a tetrahedral configuration. And that certainly is a very broad patent dealing with these type of materials. Well, nevertheless, of course, we are still involved in this type of research, because, of course, being very large pore, VPI5 is, of course, large pore, and as I said, we now have an interest in large pore material. We are also working on the transition of VPI5 into ALPO8, which is another very large pore material discovered by Union Carbide. And we like very much to work onto these systems where you can see transformations, because by relating those transformations to these structural changes, then you can really improve your understanding of the aluminum and phosphorus NMR techniques which are used to broadly characterize these materials. Well, I believe I'm now coming about to an end, because we are in let's say 89, and here is the last discovery which we made. In October 1989, and that was sort of following my relationship with Stanford and Michel Boudard, Michel proposed to me one of his extremely brilliant graduate students, who was no one else than the brother of Mark Davis, Bob Davis. So Bob Davis came to Namur for 1 year to work with me He was also acting as a bridge between Mark and myself in our work on VPI5. But Bob's task was essentially to check on one proposal that I had made the year before that was related to the direct aromatization of normal hexane on zeolite L containing platinum, platinum KL. Now that very problem started in the early 1980s in France with Denise Bartomeuf, among others, and some people at ELF. And they rapidly recognized that platinum on KL was the most active and selective catalyst for the direct aromatization of normal hexane. That work later on was picked up again by Exxon and by Chevron, and Chevron disclosed, if I'm right, about 2-3 years ago, a process under the name Aromax, where they take hexane and make directly benzene by using platinum on the potassium barium L zeolites. By the way, barium is doing nothing, it's just there for patent purposes, and we have checked that it doesn't enhance or changes the activity or selectivity of the zeolite per se. Well, sure enough, the idea was that because of the unique cage structure of zeolite L, hexane would sort of curl up in the cavities of zeolite L, and so come head to tail sort of and cyclize more easily. Bob did some beautiful work, and we reproduce, I would say, all the patent data very nicely. But the problem was still, is there an electronic effect, or is that more a conformational effect? And then, remembering my good old days with magnesium oxide, I told Bob, well, why don't we take a magnesium oxide that has been stabilized by a little bit of aluminum so that it maintains a very high surface area. It's going to be highly basic, like the L-zeolite exchange with potassium. Then we can put small platinum aggregates in it, and let's run it for comparison purpose. And to our extremely great surprise, and here I'm only a few months back in my scientific life, we observed a behavior that was totally competitive with platinum L in terms of activity and in terms of selectivity. We were certainly not expecting that by any means, nor were any of our colleagues in industry when we first mentioned that to them. And immediately the first thing which we did was to get some patent coverage, although we didn't understand why they were working, but and we got that. And we have now in press, in Nature, a paper that's going to appear in 1 or 2 weeks from now, reporting on this very unusual observation. I think it's quite important because at this stage we believe that this finding is opening, first of all, a new area of catalysis, in that it shows that basic supports have been ignored for too long. And these supports exist. We have now the means to prepare them with rather high and stable surface area. And I firmly believe that a lot more attention should now be devoted to catalysis, which this support can do, like, for example, cyclizing dienes. And for example, in the case of hexane, which we are talking about, it could very well be that the platinum would first dehydrogenate partially hexane, and then that the basic support would take over. In which case, the platinum on magnesium oxide catalyst for the hexane aromatization would be the first example of a bifunctional catalyst involving metallic and basic sites rather than metallic and acidic sites. Well, I think the lesson which we need to learn here is that in catalysis there is always something new to be found, and one also needs to keep an open mind, because of course I would have loved zeolite L to be the best catalyst and the conformational model where hexane sort of embraces head to tail to be the real one. But on the other hand, when you are faced with the observation that another system which is not a zeolite does behave as well, that is a fact, and we are now trying to understand that in more details. Well, I think I have sort of more or less summarized where I started from and where I arrived, and maybe I should stop over here.
Well, what is the biggest difference in research in Europe and the U.S.?
In catalysis, you mean?
In catalysis, in carrying it out?
Yeah, well, I think that there is a very big difference between catalysis in Europe and catalysis in U.S. Catalytic research in the U.S. has been mainly directed to petroleum catalysis, petrochemistry, and related processes. Of course, there has been a catalysis that has been conducted at Dow and Monsanto and DuPont, but nevertheless, the biggest effort were in the field of the petroleum industry. In contrast to that, you have in Europe a lot of course, smaller-sized companies, but still rather big, like ICI, Hoechst, BASF, Rhône-Poulenc in France, Montedison, Enimont in Italy. And these companies were interested in catalysis mostly to produce, well, we could call these fine chemicals on a general basis. So this, I would say, is one difference. The motivation was different. Second, there has been a clear trend in the US in the early 80s to progressively shift from catalysis to materials science. And that has been the reason for which Exxon stopped part of his research in catalysis, why DuPont stopped part of his research effort in catalysis, even all its research effort in catalysis for some time, and all going strong into materials. That never happened in Europe. In fact, the emphasis in Europe has been on the fact that a catalyst is a high added value material, that it's a high technology product which deserves a lot of interest and a lot of support. And this support is coming from industry, of course, but it is also coming from European institutions like the European Commission, for example, where catalysis has been recognized as one of the priorities with the same, I would say, support as polymers or ceramics or electronics or whatever. Catalysis is important and is recognized as a very important piece of science. And of course, this is maybe because in Europe the chemical industry represent about 25% of the national product. And so that's quite a lot of money. And most of these chemical products which are made have seen a catalyst in their life. In fact, about 90% of these products have seen a catalyst in their life. And it is now for sure the I mean, there is no doubt that in Europe the idea is now that to be competitive, let's say considering the efforts that are put in this area in Japan, and also I would say against the US chemical industry, Europe has to be strong in chemicals, and that means also be strong in catalysis. So I would say that from my viewpoint, it's rather simple to get funding if you're in a catalysis lab in Europe and if you have a rather good reputation. Much more easy than it is in the US.
How did John Turkevich interact with graduate students?
Oh, John was a very strong character, of course. He was also at that time the minister of the Orthodox Church in Princeton. So I had a lot to learn from John, both his enthusiasm, which he always had. He was really pushing very strongly. But he was an extremely human person. And I've interacted with him very regularly since then, and whenever I had an opportunity, I would go and meet him when I was even at Mobley in Princeton. No, John was really a good teacher. He was a hard worker, pushing his students rather strongly, but leaving them a lot of autonomy. He was interested in getting results because he was enthusiastic about research. But certainly I learned a lot from him, and I would say that my years, these initial years in the field of catalysis with him were really extremely important for my scientific life.
You want to start?
Mike's on?
Okay.
Okay, my name is Edith Flanagan. I've been involved for very many years in the area of zeolite and electrolysis synthesis and materials.